Hello, this is the video notes for Unit 2, Lesson 2. Please be discreet. It starts off with a jump start. In the jump start, we need to decide which one doesn't belong. But before we do that, let's go ahead and classify each number so then we can determine based on the classification of the number which one doesn't belong. So here's our different types of numbers in this graphic here on the right. So let's see where 2 belongs. It looks like 2 can be considered a counting or natural number. So I'm going to put a capital N for here by 2. It can also be considered a whole number. It can also be considered an integer, right? Positive 2 is part of the integers. It can also be considered a rational number. We can write 2 as 2 over 1. Can be written as a ratio of 2 numbers, so let's add that. It is definitely not an irrational number, but it is part of the real numbers. So this is these are all the categories that the number positive 2 belongs to. Negative 2 does not belong to the natural or whole numbers, but it does belong to integers, so we can put a Z here. It also does belong to rationals, so we can put a Q for rationals, and then it does belong to real. Negative 1/2 does not belong to the integers, but it does belong to rational, and it also belongs to real. Square root of 2 is right here, right? This is definitely an irrational number. I'm going to since it has no standardized symbol, I'm just gonna, for irrational, I'm just gonna abbreviate it IRR. So this is definitely in irrationals. And remember, real numbers include all rational and irrational, so this is definitely a part of real numbers. The last one is 2.2 repeating. So that one is not a natural, it's not a whole number, it's not an integer. It is definitely a rational number, right? Because it's repeating, like 0.33, 0.22, that's repeating. So I can definitely have it as a rational number, and all rational numbers are included in real numbers. So the way this table is set up is it's the smallest groups of numbers, like natural and whole numbers, are like it starts with really small groups, and then slowly it gets to be bigger and bigger groups until real numbers include all rational and irrational, so it includes everything above it. So now let's look at this and decide which one does not belong. And just looking at this, immediately square root of 2 is the only one that's irrational. That one definitely doesn't belong. I could also have chosen positive 2. That's the only one that can be considered a natural or a whole number, and it belongs to 5 different types of numbers. Negative 2 is the only one that is in the integers, so that one doesn't belong for that reason. And we could say that negative 1/2 is the only one that is written as a fraction. Granted, all of them, except for square root of 2, can be written as a fraction. So this is the only one that, like, visually is a fraction. And for 2.2 repeating, let's just say that's the only one that is visually written as a decimal. So there's a reason for every single one not to belong. The reason why this jumpstart is part of the lesson is we're going to need to be able to classify numbers as we build on the last lesson where we learned about what a domain is. Remember, a domain is the x values of a function, and often we need to decide what a reasonable domain is, and that's when we'll come back here and we'll look at this table and say, well, is a reasonable domain all natural numbers or all real numbers? And we'll use this notation for now to indicate our domains. All right, let's go ahead and try a few problems. So our first problem, here's our launch. Our first problem is having to do with the Library of Congress in Washington, D.C. where they often receive boxes of books to be added to their collection. Since books can be quite heavy, they aren't shipped in big boxes. On average, each box contains 8 books. If on average each box contains 8 books, how many books are received by the Library of Congress in 6 boxes? So if there's 8 books per box, we can just multiply 8 and 6 and get 48 books. In 10 boxes, we can just multiply 10 times 8 and get 80 books. Or in n boxes, that will just be 8n, which is our equation. Use a table, graph, and an equation to model the situation, then answer the questions. So our equation is going to be f of n equals 8n. This looks very arithmetic. Granted, we're not using that vocabulary anymore because now we're moving on to kind of a bigger category of functions. So rather than saying arithmetic, I would call this now linear. So I'm actually going to write that over here because that's going to be one of our takeaways at the end of this problem, that this is linear. Okay, what's the domain? So n represents boxes, so we need to think about what numbers make sense for boxes. I'll decide that in a minute after I do my table and my graph. So here's my table. We've got boxes, we've got books. And for 0 boxes, we've got 0 books. For 1 box, we've got 8. 2 is 16, 3 is 24, and so on. Okay, so let's graph that. Boxes and books. Okay, I think I'm just going to go by ones for the x-axis. This will be 1, 2, 3, 4, 5. And then for the y-axis, let's go by, I think every box will be worth 5. So let's just label every second box going by tens. Okay. So times 0, we've got 0 books. Not times 0, but 1 box, we've got 0 books. And then 0 boxes, I should say, have 0 books. And then 1 box has 8 books. 2 boxes have 16. 3 boxes have 24. So just looking at it, yeah, it's a straight line trend. This is definitely linear. Okay, now the question is, should we connect the dots? We've got boxes, we've got books. Do we have the data in between? Can we ship half a box or receive half a book? No, we can't. So this situation is definitely discrete. We're only going to have dots on there, which means that when we decide on our domain for boxes, we can't have anything that has decimals. So real numbers have decimals, irrationals and rational numbers have decimals. Integers don't, but integers also have negative numbers, and we can't have negative boxes. So I think we're left with natural or whole numbers, and it is possible to have 0 boxes and 0 books. So I think we're going to go with whole numbers in this situation. So I'm going to put a capital W, which stands for whole numbers. That makes sense. All right, let's do our second question. Many of the books at the Library of Congress are electronic. About 13 e-books can be downloaded onto the computer each hour. If about 13 e-books can be downloaded onto the computer each hour, how many e-books can be added to the library in 3 hours, in 5 hours, or n hours, assuming there's no limit on memory on the computer? All right, so let's look here at 3 hours. So 13 times 3 is 39 e-books. Okay, 13 times 5, that's going to be 65 e-books. And then for n hours, that'll just be 13 times n. So that's our equation right there. So this is looking kind of arithmetic, but remember we're using the larger vocabulary, so this is looking linear. So I'm going to write f of n equals 13n, right? That's our pattern, that's our variable, and our zero term is 0 because when 0 hours have gone by, they have downloaded 0 ebooks. So our domain is hours. We'll talk about a reasonable domain in a minute. Let's do our table. So hours, and then ebooks downloaded. 0 hours, 0 ebooks, 1 hour, 13, 2 hours, 26, 3 hours, 39, and so on. Let's go ahead and graph it. Hours, and then ebooks. Okay. For hours, I'm just going to go by ones. So 1, 2, 3. And for ebooks, I'm just going to go by fives, which means every other box I'm going to increase by 10. That way my labeling isn't so crowded. All right, let's go ahead and graph it. At 0 hours, we're at 0 books. At 1 hour, we're at 13. At 2 hours, we're at 26. At 3 hours, we're at 39. Okay, so definitely a straight line trend, which means it's definitely linear like we thought it was. Now the next question is, can I connect the dots? Can I be downloading for half an hour for 30 minutes and still get part of an ebook on my computer? Yeah, absolutely I can. So I would definitely suggest connecting the dots here and saying that the situation is continuous. Okay. All right. One more situation at the Library of Congress. Our next situation is for the librarians when they keep the library orderly. They put books back in their proper places after they've been used. A librarian can sort and shelve 3 books in a minute. If a librarian can sort and shelve 3 books in a minute, how many books does the librarian take care of in 3 hours, 5 hours, or n hours? All right, so I think we've got to do a conversion first. Let's go ahead and switch this to per hour. So there are 60 minutes in an hour, so we're just going to do 3 times 60 and get 180 books taken care of in 1 hour. Okay, so that will help us in predicting and then setting things up. So in 3 hours, 180 times 3 is 540 books sorted and shelved. In 5 hours, we've got 900 books sorted and shelved, and in n hours, we've got 180 n books sorted and shelved, which means our equation is f of n equals 180 n. Don't have to write the plus 0 because I know in 0 hours I've sorted 0 books. Our domain is going to be hours, and we'll figure that out in a moment. Oh, I forgot to do the domain for question 2. So let's go back just for a second. So over here, our domain is hours, right? And it's continuous. The numbers in between actually happen for downloading ebooks, which means that this is not just natural numbers or whole numbers. Definitely not integers because we don't have a negative portion. I'm thinking that this is positive real numbers. So I'm going to do a big plus and put our capital R because we can have decimal hours, positive decimal hours, and positive ebooks downloaded, including the decimals. All right, so over here for number 3, the domain is hours, so we'll decide that in a second. What is a reasonable domain? So we're going to have hours and books shelved. So 0 hours, 0 bookshelves, 1 hour, 180, 2 hours, 360, 3 hours, 540, and so on. Okay, let's go ahead and graph that. So over here we'll have hours. I'm going to do this one a little bit differently. And over here is books shelved. So I'm going to go every other box will be 1 hour. One, just to kind of spread it out. And I'll show you why in a moment. And then over here, let's go every other box is 100 books shelved. That will also spread out my y-axis. All right. So let's graph it. So at 0 hours, we've got 0 books shelved. At 1 hour, it's 180. 2 hours, it's 360. 3 hours, it's 540. So right there. So again, this looks linear, right? It's a straight line trend, so I'll write that down. This is linear. And then the question is it discrete or continuous? Can I connect the dots? So let's think about the librarians shelving the books. So we know every hour they do total 180, but we also know that every minute they do 3. So we actually do have some data in between. We know on the minute what's going on. So I can actually add a dot for each minute. I'll just try to add a whole bunch of dots. And these little dots represent what's happening on the minute. And then the question is, okay, if I know what's happening every minute, can I connect the dots now? Well, do we know what's happening like even for a smaller amount of time, like on the second? Can we break it down even more into like that decimal of an hour? And we don't really know, do we? So I think that this is still discrete, even though like we've kind of filled in between 0 and 1 hours, but we can't connect all those little dots because we don't know what's happening smaller than on the minute. So I'm going to say this is discrete. And over here for our domain in hours, or I'm going to just change it and say time, I'm going to say that it's going to be whole numbers for every minute. Okay. All right. Let's do a little bit of review. Would it make sense in any of these situations, this is number 4, for there to be a time when 32.5 books were shipped, downloaded onto the computer, or placed in the shelf? So the only situation for like this decimal amount of books would be for downloading onto the computer. All right, number 5. Which of these situations, problem 1 through 3, represent discrete and which represents continuous? Justify your answer. So we know number 1 is discrete. And the reason is we do not have decimal boxes or books. So boxes and books can't be decimals. Okay, that is pretty much the same thing for, so that's number 1. Number 3 is also discrete, kind of for the same reason, except for this time we've got hours and books, but it's not really hours and books, it's really like we know on the minute what's happening, right? So I'm going to say minutes, and books can't be decimals. Which means the only one that can be decimals is number 2, that was continuous. And for that, it was hours and ebooks, which could be decimals. All right, so that completes the first part of this lesson. Now the second part of our lesson is looking at two more situations. So let's go to number 6. Number 6 gives us a giant piece of paper, and it's cut into 3 equal pieces, and then each of those is cut into 3 equal pieces, and so forth. So when we've got 0 cuts, we've got 1 piece of paper. When we've got 1 cut, we've got 3 pieces of paper. When we've got 2 cuts, we've got 9 pieces of paper. So this looks different than 1, 2, and 3. This task looks like it is not linear. This looks like it is exponential, right? Because we're timesing by 3. There's a times by 3 pattern going on. Okay, that means that I'm going to pull on what we learned in Unit 1. I'm going to write an equation that has our starting value. At 0 cuts, we've got 1 piece of paper. It's got our pattern, 3 times 3 each time, and then our variable is n in the exponent. Here's our table. This is cuts, and this is pieces of paper. Okay, so at 0 cuts, we've got 1 piece of paper. At 1 cut, we've got 3. At 2 cuts, we've got 9. 3 cuts, we've got 27. Okay, let's go ahead and graph that. So cuts, and then pieces of paper. Okay, so for cuts, I'm just going to go by ones. So 1, 2, 3, 4. And then for pieces of paper, I need to get up to 27. So let's go by 5s, and I'm only going to label every other box. So looks like that. Okay, and then let's graph it. So 0 cuts, 1 piece of paper, 1 cut, 3 pieces of paper, 2 cuts, that a tiny bit higher. 2 cuts is 9 pieces of paper, 3 cuts is 27, and if we did 4 cuts, that would be all the way up at 81. So you can kind of see we've got a curved pattern here. It's definitely increasing. So we could classify this as exponential. And then the question is, do we connect our dots? Do we have information in between at like half a cut? Not really. So that confirms that we just leave it as dots, and this is going to be discrete. All right, what is a good domain for this situation? So domain, remember, is the x values. 0, 1, 2, 3. That looks like whole numbers. Would it make sense to look for the number of pieces at 5.2 cuts? No. The situation is discrete. We have no decimal cuts. No decimal cuts. Would it make sense to look for the number of cuts it takes to make 53.6 papers? Same argument, right? We have no, there are no decimal papers. All right, let's turn the page to number 7. Okay, number 7, it says medicine taken by a patient breaks down in the patient's bloodstream and dissipates out of the patient's system. Suppose a dose of 60 milligrams of anti-parasite medicine is given to a dog, and the medicine breaks down so that 20% of the medicine becomes ineffective every hour. So we've got a percent, right? That's definitely, if we talk about our vocab from Unit 1, that's definitely geometric. And when we talk about losing 20% effectiveness, our common ratio is actually what we're keeping. So we're losing 20%, we're actually keeping 80%. So ours is going to be 0.8. All right. Okay. how much of the 60 milligrams dose is still active in the dog's bloodstream after 3 hours and 4.25 hours and so forth. So let's write our equation and then we could go back and do those predictions. So it starts at time 0 with 60 milligrams. We're keeping 80% every hour, and this is exponential, right? So our variable is in the exponent. Okay, so I'm going to actually do the table first because maybe some of these other values will show up in our table. So this is hours, this is milligrams. So at 0 hours, we've got 60 milligrams, 1, 2, 3, and then let's put 4.25 here. All right, so I'm gonna grab my calculator, and all I do is take the equation, 60 times 0.8, and I'm gonna replace n with the hour. So I'm gonna write 60 times 0.8 to the first power, right? That's for 1 hour, so I've got 48 milligrams. And then I'm going to replace the n with 2 hours, so I have 38.4 milligrams, and then replace the n with 3 hours, and I'm at 30.7 milligrams left. That's effective, and then I can just replace the n with 4.25 in my equation, and that will get me 23.2 milligrams at that time. So this is kind of telling me that I can predict at any time how much medicine is still effective in the dog's bloodstream. So let's go ahead and graph this and show that we can predict at any time, even decimals. We'll show that on our graph. So here's milligrams. Milligrams, we need to go up to 60, so I'm just going to go by fives and then label every 10, so every other. So that'll be a nice scale. And then for hours, I'll just go every other box again. That seems to be nice. Okay, so times 0, we've got 60 milligrams. And then at 1 hour, we've got 48. And then 2 hours, we've got 38.4. So that's like over here. And then 3 hours, 30.7. That's like just above right here. So it kind of looks linear, but it's not. It's not linear at all. You see we've got like this big jump here between 0 and 1 hours. It's dropping 12 milligrams. Here it's dropping 9.6. Here it's dropping 6.7. Here it's dropping, how much is that? Oh, this is 7.6, my bad. And then here it's dropping, but that's not a full hour of drop. That's an hour 0.25 of drop, but it's like an uneven drop. So it's definitely going to be a curve. So I'm going to show like a gentle curve, and I'm going to connect my dots because I can find at any time, right? Any decimal hour, I can find how much medicine is still viable. So this is definitely continuous. Exponential continuous. Okay, which means what's the domain of the function? The domain of the function is going to be positive or rational numbers. So positive, rational, and we're going to include 0. Okay, which means we can have any decimals. We could probably even have irrational decimals, like one that go on forever. So I'm actually going to change this. No, R is for real numbers. This is fine. This is positive real numbers. Totally works. Including 0. Okay. Would it make sense to look for amount of active medicine at 3.8 hours? Absolutely. The situation is continuous. Would it make sense to look for when there's 35 milligrams of medicine? Sure. It's continuous. We can predict anywhere along that curve. Okay. All right. Let's move on to the last few questions and then our takeaways. So number 8 says, what needs to be considered when looking at a situation or context and deciding if it fits best with a discrete or continuous model? So for discrete, a quick way of thinking about it is the change happens all at once, it's countable, and we have no decimals. Okay, continuous. The change happens continuously, it's measurable, we do have decimals. All right, create your own example of a discrete word problem. So that's up to you. Create your own example. Create your own example of a continuous word problem. Again, up to you. So I'm not going to fill that in. You come up with your own. Which of the functions modeled in this task are linear, which are exponential? So number 11. Linear are number 1, 2, and 3. And exponential were number 6 and 7. And the biggest reason is, regardless if it was dots or connected with a line, linear is a straight line, whereas exponential is a curve. Okay. All right, let's move on to our takeaways. Right, so our takeaways is this table, and it talks about how we see discrete and continuous in all these different ways. So in context features, discrete is when change happens all at once. Change all at once. Okay. And our inputs and outputs, so both x and y, are countable. Okay, how do we see this in a table? For discrete, our table is really just going to have set numbers in it, right? Nothing in between. So like 1, 2, 3, and then our function is going to be like 4, 6, 8. There's nothing in between. For equations, graphs is next. For graphs, it's going to just be dots, right? Whether it's in a straight line or a curve, it is just dots, right? There's no data in between. For equations, we can actually write both recursive and exponential. So I'm going to do a linear example. So f of n equals f of n minus 1 plus 2, which explicitly could be written as f of n equals, let's just write 2n plus 1. And then the way we would see this in a domain would be something like whole numbers, which would be capital W and would look something like this. It would be curly brackets, 0, 1, 2, 3, 4, and I would do a dot, dot, dot just to show that it goes forever and close my curly bracket. So those are all different ways we can see discrete functions. Now we're going to switch to continuous. and just go through each type again. So for context features, continuous has, so the change is constant. So change is, I'm just going to use the word, I guess, is continuous. Okay, and here are inputs, and outputs are measurable. Okay, so how do we see this in a table? Well, it doesn't look so different from discrete, but you do have in between values, even though it's not super obvious, like 1, 0, 1, 2, and let's say I've got like 1, 1.25, 1.5. We can actually determine what's happening at 0.5, and it exists, right? Whereas in discrete it didn't. It was just, that's the table, it's done. So how does this look on a graph? So I'm just going to do a linear version. It is all connected, right? All our dots are connected with a line. For continuous, we cannot do a recursive version because recursive is for sequences, and sequences are only discrete functions. So if it's a continuous function, I can only use an explicit equation. So I would write something like f of n equals my pattern 0.25n plus my zero term. How would this look like in our domain? Our domain would be something like, let's do all real numbers. So I'll show you the notation for that. All real numbers. So we could do that by doing capital R, or we can do something called interval notation. So if all real numbers, that's like all negatives through 0, all positives. So we can say from negative infinity, comma, to positive infinity. That is interval notation for a domain. Okay. All right, let's go to our back page of our takeaways and just fill in a little bit of notation. Okay. All right, so we're going to talk a little bit more about this interval notation that I just barely introduced to you. This is used only for continuous situations. Okay, so I'm going to write continuous next to interval notation. Okay, and what we write is, we would write parentheses, negative infinity to positive infinity. And basically that is saying where our values start. So like the left symbol or number is telling where our domain starts, and the right number is saying where it ends. What would we say if we wrote something like that? We would say the domain is all real numbers from negative infinity to positive infinity. And well, what does that mean? That means that n can be any number between negative infinity and positive infinity, and this includes decimals. All right. Set notation. How do we write this? It looks like this. It's like in curly brackets. We go 0, 1, 2, 3, ... Okay, close curly brackets. And how we would say that is the domain is the set of all whole numbers, right? Because 0, 1, 2, 3, 4, so on is whole numbers. Okay, and what does that mean? That means that n can be 0, 1, 2, 3, and so on. But can't be any decimals in between. Can't be decimals. Okay. In this lesson, we model linear and exponential functions and learn to identify features that allow us to determine whether a discrete or continuous model is more appropriate. We discuss number sets and use them to write function domains using interval or set notation. I wish you good luck on your practice.